Hello everyone, this is section 10.3 examples part 2. So in question number 6, we are building a binary search tree for the words that we have below using the alphabetical order, and we're going to insert them in the order that is listed. So we have the words pepper, cucumber, broccoli, cauliflower, sweet potato, zucchini, mushroom. So to draw a resulting binary search tree, we're going to use the recall, left child, less than parent, less than right child alphabetically. So first and anything, we're going to have pepper. Pepper is going to be the root node. And then we're going to go, we're going to check the next letter, the next word, which is going to be cucumber. Cucumber starts with C, and C is a letter that is before P, so it's going to be to the left. So we're going to get here cucumber. Now left we have broccoli, and broccoli is going to be to the left of cucumber since B is to the left of C. So we're going to go with broccoli here. Now we have the next one is cauliflower. Cauliflower is going to be to the right side of broccoli since C is bigger than B. So we're going to have cauliflower here. Now for the next we have sweet potato, but sweet potato it starts with S, and S is to the right side of P. So we're going to use here sweet potato. That's going to go in here. Then we have zucchini, and zucchini of course is to the right of S since it starts with C. So we have zucchini. Now we have mushroom next. Mushroom is going to be to the left of pepper since M is less than P, but is going to be to the right of cucumber because mushroom is actually start with M. That is going to be to the right side of C. So we're going to have that mushroom goes here. Okay. And so that concludes the creation of the binary search tree. Now, in the binary search tree of problem 6, we want to know what sequence of words produced by an in-order traversal and what properties this is going to demonstrate. So remember that the in-order traversal is the L and R order, and that will go with broccoli first. Since that will be the node that is here. Then we got cauliflower, which is the leaf. And then we go up to the next node, which is the cucumber. And then we go to the leaf, which is mushroom. And of course, we go back up to the main node, which is pepper. And then we get sweet potato and zucchini. So we're going from the elements on the left to the elements on the right. We go first with the leaves, gets to the node, get to the right side, leave, get back to the next node. Okay. So when you think about it, this is the alphabetical sorted order, and this demonstrates that in order traversals as a binary tree is always going to yield in a sorted order, because the binary search tree is going to guarantee that all left descendants are smaller and all right descendants are larger than any given node. All right, so now let's move to question 8. So here in question 8, we're talking about a single elimination tournament with n players, and this is going to be modeled as a full binary tree. So first, why is this a full binary tree? Well, think about it. Each of the matches is going to be the internal vertex, and is going to involve 2 players, which is going to be considered inside of the tree the children of who one of those is going to advance. So every non-leaf vertex has exactly 2 children. So the way that you go for this is you can think of this root node as the final, and then you get a semifinal here, and then you have encounters before. And so this is always, when you're modeling a tournament, to get to the final, you're always going with binary, with a binary situation for each of the encounters. Now, if in part B, if there are 16 players, then of course, because this is a tree, the number of matches is going to be similar to the number of edges here. So for a full binary tree, the number of leaves is going to be 16, and the internal vertices, which are going to be the matches, are just going to be 16 minus 1, which is going to be 15. The height of this tree here is going to be given by the log base 2 of 16, which in this case is going to be 4. We don't need to make a ceiling of this or anything, since this is going to be give me an integer number. And in general, if you generalize this, where you have n players, n is the power of 2, we can write all this in terms of the number of matches and the number of rounds. So we can just generalize this idea. Okay, so the number of matches will be n minus 1. And for the height, we'll have the log base 2 of n. Okay? So that is the way that we can define that binary tree. Now, for question number 9, we want to know if this is true or false and explain the reasoning of each. We have that every tree is a forest, and this is true. In general, a tree is a connected circuit graph, and a forest is a circuit-free graph. So since a tree is a circuit-free, it satisfies the forest definition. It's a forest containing of one single tree. A tree is a forest with a single tree. Remember that the only difference between trees and forests is that forest is just going to be a bunch of trees that are disconnected components. But in general, we can just consider a single tree as a forest of a single tree. Now, every forest is a tree. This is false. We don't have the other way around, because a forest can have 2 or more disconnected components. So it can have forest can have 2 or more connected components. And hence not connected. And the tree, by definition, needs to be connected. For C, we have a connected graph with n vertices and n minus 1 edges must be a tree. This is true. And this is exactly the criteria for getting a tree, for deciding that something, a connected graph, is going to be a tree. Notice that this is the converse of the n-1 tree theorem. But there's a important assumption here is that this is a connected graph, which is what is going to make D false. Because for D, we have that a graph with n vertices and n minus 1 edges must be a tree. This is false. If it's not connected, it doesn't need to be a tree. In particular, you can have a connected component that is going to have a circuit inside. And because we're not necessarily saying that this is connected, then you can have one of the components that is going to provide for a circuit. Now, for E, we have in any order traversal of any binary tree produces a sorted sequence. This, in general, is false. In order traversal is only for binary search trees. Okay, because binary search trees enforce the property that you gotta go left, root, right. So this is gonna induce the sorted sequence. But if we don't have a binary search tree, then it's not necessary that you're gonna have a sorted sequence. Okay, so now let's go to question 10. Now, here we have a binary tree traversals that produce the following order. We have the pre-order A, B, D, E, C, F, and the in order D, V, E, A, F, C. Now, when we're talking about the pre-order, the first node is always going to provide me the root. So that means that A is going to be the root node. Now, if I go with the in order, notice that we're always going to have the node, the root here. This is my root. Then this is going to go to the left, and this is going to go to the right. And this is the order in which the children are going to be assigned. And of course, this is going to depend on the order. So after A, we should have B. Since in the DVE, this is going to be the root node, the next node, and then we're going to have D and E here, and on the other side we're going to have F, and then from F, we're going to have C, not F. C goes first in order, and then we're going to have F. Notice that that's because this is going to be a leaf and this is supposed to be the node. The same way here, B is supposed to be the next root node, and D and E are going to be the leaves for the in order. Now, if we're going to write the post order traversal, then we just need to check how we're traversing in this particular order. So the post order will start from the leaves. So we're going to have D, E, and then go to B. And then I go to the other side and then go F, C, and then finally I go to the root node A. So this will be the order. So D, E, B, F, C, A. Okay, so that concludes the examples of section 10.3.